Okay, so we can start first presenting the schematic representation of this example. So today's theme is again I'll call coordinate partitioning. And as I said, we're going to go through an example which should be represented here. I think it's this one. Yep. So as you can see here, we have a slider crank mechanism. Okay, so it's composed of 4 bodies, which we can directly number here. So we have body 1, body 2, body 3, and then body 4. No? So as I was anticipating, it's a mechanism that converts rotary motion into translation. So observations. So it's 4 bodies, as I was saying. And this means that since we are in the 2D domain, this basically means that we have how many geometrical parameters in theory, apart from constraints, to describe this motion, this system. Anyone? 4 bodies in 2D. How many parameters do you expect? Well, we said it's in space, it's 2 translation and 1 rotation for each body. We have 4 bodies, so it's 3 times 4. No, it's 12 parameters. So it's 12 coordinates expected to describe the system. So how many constraints do you see here? Hi. Please don't close, just keep it like that so people knows that it's not closed. So how many constraints do you see here? Well, for example, let's name it, okay? Let's go with green. So I would say here we have a clamp. So we have 8 constraints. No, that's too many. Well, I mean, I'm not talking about the number of equations. I'm asking the number of constraints as a whole. Okay, so for example, here I see a revolute jaw that's a hinge. Okay, as we know, in this case, it's a composition of 2 scalar equations. Okay, but apart from the number of scalar equations which represent each constraint, how many constraints do you see here? 5. Correct. Why 5?
2 for the first one, string. 1 more for the second.
So would you please say which ones are here for the first bodies? What are the constraints that you see? So here I have a ground constraint because this part here, part 1 is fixed on the ground. So let's say how many So we said five constraints. Okay. In order not to confuse you, yeah. So let's call five. So please be able to distinguish between the number of constraints and the number of constraints equations. Okay. So here we're going to have, as your colleague was saying, 5 constraints that we're going to go through now. But to each constraint, we're going to associate more than one equation. Okay, so one constraint can be in theory, characterized by up to, in this case, in 2D space, up to 3 equations, right? Because it can enforce a condition over the 2 displacement and 1 rotation. Okay. So here we are talking about constraints, okay, number of constraints, not the number of constraints equations. Huh? So 5 constraints. So let's see which ones are they. So we have one ground constraint. Okay. Which, as I was saying, we can exemplify like this. So that's our ground constraint. Then how many hinges do you see? Well, one in O, right? In A and in B, so 3 of them. So it's 3 hinges or revolute joints, which we can just call like that. So one is here, the other one is here, and the third one is here. And then we have one additional constraint, which is here, no? The fourth body has to slide over, the ground. Okay, so this is a constraint too. So this fourth body cannot, rotate as it wants. It can only go from left to right and vice versa. So it's a slider. And this is called a tray, right? It's a tray, carrello. And this typically is, represented like this. That's the tray, right? So here we have a tray. Oops. So already now, you can try to see how many equations are there. So from here, if you actually slide it here, you can go in 3. Constraint equations. How many constraints equations do you see, which are needed to enforce those 5 constraints?
Going the other way. The body can only move in one direction.
So you're reversing it. That's not the way to do it. Yes, but yeah, you can do that, of course. Well, 11. Why 11? It's easy, no? Come on, here we have the fixed one, which removes all, the possibility to move. So it's 3. Then we have 2 for the hinges, right? Because the position of the 2 points must coincide of the 2 bodies. So we have to enforce an identity, condition for the position. So it's 2 equations. 2 equations. 2 equations. And then here, how many? It cannot rotate and it cannot go up and down. It can only slide. 2 more, right? So if you add it, it's 11, right? So we have ground constraint. We said it's 3. equation. Then we have hinges. It's 3 times 2, no? 3 times 2 equations. And then we have a slider or tray. It's 2 equations. And this means that our number that we called NC in the previous lesson, so NC for us is 11. Okay, NC is 11. So again, the Grubler count is 1, as you said. And this is expected, no? Because eventually, the only thing that, the only motion that this mechanism can do is actually moving left and right the body forward, right? That's the only thing. Okay, so this is the first analysis, okay, that we have to do. Okay, this was pretty easy. Let's actually now define the coordinates, right? So let's do it like this. So this was the first phase. Now we're going to define the coordinates. So the number of independent parameters that we have to expect, or degrees of freedom, is 1. 1 degree of freedom. Can you get what is the actual meaning of this? It means that you can only set one parameter freely, arbitrarily, and all the other 11 will follow. That's the meaning. And in fact, if you think about this, in the physics of this mechanism, typically you have an engine here on point O, which is fixed on the ground. It rotates, and it transforms the rotation into a sliding motion. Okay, so you basically govern this mechanism, making, imposing the rotation of the body of the crankshaft, basically, from O to A, in its rotation about O. Okay, very good. Now let's assign the general coordinates. Okay. Oops. So. Okay, so for body 1, we have, one thing, this can be useful for you. Many times, the bodies within a multi-body system are referred to as links. Links. Because typically they link different points. So the first body, which is the first, I'll call it the frame, if you want, or the bracket. Let's call it bracket. So it's first. Let's do like this. It's going to be R1, R2, and theta 1. Sorry. Oop. So these are the components. But again, it's going to be for body 1. So, as you know, It's the superscript. So the superscript defines the body. The subscript is the component. Of course, the angle doesn't have a component, so it has no subscript. Huh? So body 2, we'll call it crankshaft. Two is, of course, the same thing. So then we have body 3. And this is, let's say, the road, connecting road. It's done like this. And then, of course, we have the fourth body, which is the sliding mass. Okay, so now our vector of generalized coordinates, we can arrange it like this. Okay, this is our Q. We put everything together. Okay, that's very easy. Okay, as we said, so we have 12 parameters, but only one is actually arbitrary. Okay, it can be set arbitrarily. Now, let's actually see how to enforce these constraints. Okay. Here are the equations, okay? All right, so let's start with the ground constraint. Huh? How would you impose the first constraint about the ground constraint, given the coordinates that we have defined? Or which one? So we have this one. Then I would say this one. And also the angle, right? So this is the ground constraint. And we see, as we said, that we have 3 equations. Now we have a hinge at O. At point O. How would you enforce it? If you look at the picture, that we can always have it here as well, just for helping us out. We have a hinge at O. We already saw how to do it. We saw it yesterday or 2 lectures ago. we have to say that basically point O, when described with respect to body 1 and to body 2, it has to be the same, right? So we can write it like this. We can say that before actually saying that, just a second. Yeah, okay, yeah, sorry. Yeah, so we could say that R1 plus A1 R1 0 of point O over bar must be equal to R2 plus A2 R0 of point O with respect to 2, right? This is the hinge. But there is one more thing that we did. You see, I went through a step maybe through too fast. But when you have, the first thing that you have to do when you analyze a system of bodies is defining the local frames. Okay. And here we already did it. Okay. But look, so you see, this here is the body frames of the first link, which is basically the engine, or what we call bracket, fixed on the ground. And point O is exactly at the origin. Okay. So now, if you consider this point, for example, this point O, to coincide also with the origin of the inertial frame. Okay, so that you can say something like this. This is actually, let's do it like this. So that this is your x2, for example, and this is your x1. Then this first part here would amount to what? This is the position of point O given with respect to the body 1. So, right? Why is it 0? Because this is 0 because it's the center of the local frame, and this is 0 because it's the center of the inertial frame, right? So this is 0. Just to simplify. Then hinge at point A. That's just the same, so I will go through it very quickly. So it's what? R2 plus A2 of R0 point A with respect to 2, where I should say it's equal to the other thing, but I could also write it like so. Like this. Okay. Then we have the hinge at B. And this is just the same, so we're going to go R3 plus A3 R0 B minus R4 minus A4 R0 4 of B. Huh? And then we have the sliding. Please move here. Let's have everything just in the same slide if it's okay with you. So we write down here. Or actually we call it tray, I remember. So tray. How do we enforce the tray? Well, any idea? The tray means that body number 4, so the sliding mass, cannot rotate, it cannot go up and down vertically. So I would say R4 to 0, theta 4, 0. Is that okay? So but the body number 4 cannot rotate, 1, and it cannot go up and down. So the vertical component has to be 0. Okay, now the next step is to put these equations in the following form. So we want to derive something of the form that we saw yesterday. So delta, so virtual displacement of the dependent equal to C di delta y. To do so, we need to define what? We need the Jacobian, and then in particular from the Jacobian, doing the partitioning, the part of the Jacobian which is associated to independent coordinates, and then the part which is associated to dependent coordinate. Why do we do that? Why do we want to do that? Because eventually we want to do one thing at the end of this exercise, being able to express in a matrix form like here, the dependent coordinates in terms of the independent, so that I straightforwardly get the dependent coordinates once I set the independent ones. Okay, that's what we want to do. So we have a mechanism, we have some bodies, some constraints, they are interconnected the one with the other somehow, that we have seen. And the idea is, okay, but how, once I choose the arbitrary, the independent coordinate, how can I get straightforwardly the dependent ones? To do so, we need to get this. And to get this, we need this, as we saw yesterday.
That is CDI?
Yeah, CDI. Dependent, independent. We introduced it yesterday, in yesterday's equations.
I just wrote normally C. So it includes D and I both.
Yeah, it's from yesterday. Let me go back to yesterday's. So this is. So let's go back one step. Let's recap. So we want to express the dependent coordinates in terms of the independent ones. That's our goal. So since this is our goal, we proceed as we saw yesterday. So we saw it yesterday, CQ dq is equal to 0. This is what we saw yesterday. Okay, so this is the Jacobian. Okay, but from here, through a partition, so this is coordinate partitioning, so you choose which one is independent, and so all the rest will be, in this case, dependent. You can rewrite this like this. So CQI delta QI plus CQD so this is just exactly the same thing which I have written. So this is, as we remember, this is an NC times NC. This is an NC times 1. This is an N minus NC times 1. And this is an NC times N minus NC. Okay, so this is what we saw yesterday. Now, from here, we have that delta Q, the dependent, the virtual variation of the dependent ones is what? Is minus CQD to the minus 1 applied over CQI applied over delta QI, which is, we've called this as CQDI or CDI as you wish. I think, yeah, CDI delta QI. Okay, so this is what we want. So that now, as you already observed yesterday, here we're talking about virtual variations. Okay, so why are we actually focusing on virtual variation rather than actual, dependence of pointwise dependence of the variables? So why is there a delta here? What do we actually need this delta for? This is going to be clear, if not today, on Monday, because we eventually actually need this more than to relate the virtual variation of the coordinates rather than the coordinate themselves, okay, pointwise. But eventually, so what we want to do here is actually, correlating the dependent and the independent, so that once I set this, I, straightforwardly get this. All right. Because then is this that I need to enforce the equations of motion. All right. So how to do that? So in order to be able to get, the CQ, the Jacobian, in order to get, the CDE, we need to start with the Jacobian. So we need to implement this first step. So we have to derive the equations. Okay. So from here, if we want to start from here, so to get the CDI matrix, we have to start from the derivation of the Jacobian. No? This is the first step. To get the Jacobian, we have to derive, as you can see here, the constraint equation, okay? So, to get CQ, we need to derive the constraints. Because you remember that we have something that goes like this. We saw it yesterday. And then there is a virtual derivation, the virtual derivative, so that this becomes the C over the Q times delta Q equal to 0. And this is actually, as we said yesterday, this is C Q delta Q. Right? So we need to estimate CQ, which is equal to the C to the Q, right? So this is what we have to do now. So derive the constraint equation. I will call it constraint equation, like this, for the ground constraint, okay? So let's start from there. Well, how do you do that? So remember that we had something of this form. R1, 1 equal to 0, R2, 1 equal to 0, theta 1 equal to 0. That was the ground constraint. So you apply a delta, where this quite straightforwardly becomes delta R1, 1 equal to 0, delta R2, 1 equal to 0, and delta theta 1 equal to 0, right? Or if you want to put it in a matrix form, you can write this like so. So 1, 0, 0, 0, 1, 0. This is very easy. Right? Super easy. Okay, now let's go with the second one. What are we going to do here? You see, I'm deriving the first one, then we're going to go through all the hinges. Why? Because doing this, you see, this is delta, delta Q1. Okay, is delta Q1. And so this will, if you want, you could call this as CQ, the Jacobian of only the first body. Okay. So if you go through this for all the constraints, and then we assemble these parts here, these Jacobian which are given for each constraint, we assemble them together, then we eventually come up with the Jacobian of the overall system. Okay, that's, you see where I'm going. Okay, so let's do it. So here we said derive. Of the hinge at B. So we have something of this sort, if you remember. We have R2 plus A2 R0. No, hinge at O, sorry, the point O. Right? So if I derive it, I get the following: delta R2 plus what? The derivative of A2 with respect. I should write, okay, let's write it everything. So the Q, okay. But you see, the matrix 2, A2, it's only dependent on the theta, right? So when I do this derivation with respect to Q, this partial derivative with respect to Q, I could just write it like this. It's exactly the same. And so here I'm going to write delta theta 2 times, then I should also derive R0O, but this is a constant, it doesn't actually depend on anything. So this is going to stay when I do the derivative. Okay. This is equal to 0. Clear? Okay. Now let's calculate. So if A2, we already saw this rotation matrix in the 2D plane is something of this sort. So this is also called or denoted as A2 theta. This is typically denoted as A2 with a subscript theta, okay, which denotes the derivation with respect to theta. So we say that A2 theta is equal to what? Well, right? So if you do the end, R0, 2 of point O, look at the let's put again this picture here. So you see where I am at with the second frame. So this is our R0, O, 2. Okay, it's that vector there. Okay, going from the origin of the local frame of the second body, reaching out O, right? So if we assume that the length from O to A is equal to L2, if we say that OA in terms of the modulo of the vector, we can call it L2. Then what are the components of the vector R0, 2 of point O? Can you guess? I would say that of this vector here, so R0, 2, I mean, these are, since it has an overbar, it has to be expressed in the Logar frame, right? In the Logar frame of body 2. So what are its components? And the body frame 2 is done in this. Huh? Okay. Exactly. So if you want to rewrite it in matrix form, as we did for case 1, if you do all, if you write this equation here in matrix form, so equation 1 becomes one, 0, L2 divided by 2 sinus of theta 2, 0, 1, minus L2 divided by 2 cosinus of theta 2, applied over what? Delta R1, 2, delta R2, 2, delta theta 2 equal to 0. Okay? Is this clear where this comes from? Comes from here. Here. If I write this, substitute everything here, and then I try to write it as a matrix multiplication, you get this. And so this is again Q2. Of course, the same goes for the hinges at point A and B. Exactly the same. So we had, for point A, we had, if I remember it correctly, like this. So this is basically the same as before. It's just changing the point of application. So the only thing that changes is actually this R0, 2, because now it's of point A. It's going to be plus L2 divided by 2. And then for point B, exactly the same, just a change in the subscript. Again, we have a derivation. Okay, no surprise. Now we put it in matrix form as well. The only thing that here changes is this. So R0, let's see, we have this, okay, R0 of point A and B with respect to 2 and 3. Okay, so R0 of point A with respect to point 2 is, as we said, L2 divided by L divided by 2 and then 0. R0 A of with respect to 3. If you look at the join is minus L3 divided by 2, where L3 is defined exactly the same way, right? Because the frame is in the center as well. And then we have R0B in 3 is L3 divided by 2, 0. And R0, 4, the point B, is what? What is it? Looking at the picture. Get a look at the, you can look at it as well another time. Right, because it's exactly the fourth reference frame, log reference frame is actually centered in B. So that's why it's 0, 0. Okay. Okay. So in matrix form, again, so hinge at A is 1, 0, minus L2 divided by 2 sinus of theta 2 minus 1, 0, minus L3 divided by 2 sinus of theta 3 Here we have 0, 1, L2 divided by 2. Okay, multiplying what? Well, all the variables, the general coordinates which are involved in the definition of the hinge at point A. So what are they? They are delta R2 and delta theta 2, and then we have delta R1 3, delta R2 3, and then delta theta 3. Equaling 0. Two equations, right? So we do the same thing for the hinge at B. Can I slide? One, 0, minus L3 minus 1, 0, 0. Then here we have 0, 1, and 3 divided by 2, 0, minus 1, 0. And again, it goes like this. Delta okay. Then we have the last one, which is sorry, oops. For the trade, So we have if we derive it and in matrix form, it's very simple again. Okay.
Delta R1 would be
I'm sorry? No, no, no. Yeah, you're correct. I will put it like this. Huh? Okay, yeah. Okay. Okay. So now we have all the submatrices. Let's assemble now the Jacobian of the system. So this is gonna take some time because it's all right. I'll try to do it as so. This is a this is an 11 times 12, right? Matrix, yes. So it's quite big. So I'll take all the screen here. Okay, so it's like this. Okay, so it's 11 rows, and then we have 12 columns. Why 11 rows? Rows 11 are the constraints equations. So every row is a constraint. And 12 columns because they have to be expressed in terms of the 12 general coordinates. Okay. I'm just assembling the matrices that we have already found, but expressing them all in one matrix with respect to all the generalized coordinates. Okay. I know it's tedious, but it's gonna be useful. Oh, no, sorry. Sorry. It's 0, 0, 0. Then we have L2 divided by 2 sinus of theta 2 minus L2 divided by 2 cosinus of theta divided by 2 minus L2 divided by 2 sinus of theta divided by 2, and then again L2 divided by 2 cosinus of theta 2, then 0, 0, 0, 0. Okay. All right. Then we have the other one that I was writing. So it's 0, 0, 0, 0, 0, minus 1, 0, 1, 1, 2, and 3. 0, 0, 0, 0, And then here we have the other one. Cosines of theta 3. And here we have a minus 1. Hmm? And then eventually the last one, finally. And that's it. Okay, I know it's a big one. You don't actually need to write it because it's in the notes. I mean, if you want, you find it in the notes. But so this is the matrix. At this point, you have the most important decision that you have to take so far. And this, please keep it in mind because it's a very important concept. When you have a certain number of constraints equation, in this case we have, as I said, 11 constraints equations. So here we have 11 rows and 12 generalized coordinates. So this is an 11 by 12. The choice of which one is your arbitrary parameter, your arbitrary coordinate, is your independent coordinate is arbitrary. So you can choose whichever you want among the 12 parameters to be the independent ones, and so consequently the rest to be dependent. Okay, it's not prescribed a priori. You have 12 equations, 12 coordinates. One you choose, the other one will follow. Which one you want to choose so that the other one will follow, it's up to you. Okay, and this choice must be done in a smart way. Okay, so that the formulation can be as easy as much easy as possible.
In our case, isn't it R4, R14, the independent?
Go ahead.
The independent, the one that we want to choose, we'd like to choose R14, R24, R4, right?
Let's take a look again at the. Yeah. So this is our system, huh? If you remember. So which is the motion in this mechanism that you want to set arbitrarily so that all the other parameters will follow? Typically, the choice is to be done in such a way that the arbitrary parameter, the independent coordinate, is the one that we input in the system, right? So which is the one which we input in this system? It depends on how the system will work eventually. But typically, as I said, this is done to convert rotary motion into linear motion. So which is the one parameter that we will input inside the system?
We want to convert rotary motion.
Yes. No, theta 2. Theta 2, right? That's our arbitrary motion. But as I said, nothing will forbid you to choose otherwise, and we will see. Okay? And this has consequences. So if we choose θ2 to be our arbitrary variable, to be our independent coordinate, so if you remember, θ2 in the number of equation was the sixth. So it means that if we go up and we up to the sixth column, that gives us our CQI. Okay, so this, which is the sixth column, yes, thank God. This one is our sixth column, and therefore is our CQI. So from CQ, the way to actually derive smartly the CQI and the CQD is that CQI is nothing than the association of the columns which have the number, whose number is the same of the independent parameters of choice. So if, for example, we had the sixth and eventually also θ4 as independent parameters, I'm guessing, then our CQI would have been the association, the conjunction of the sixth column and the 11th and the 12th column, okay, together. That would have been your, and CQD is what is left. Everything that is left is our CQD. Okay? Now, let's write it. So the choice of so because here, as I was saying, we are partitioning, okay, between independent and dependent. Okay, so that's the point. The choice of the coordinate is arbitrary. We choose θ2 as it's the parameter that we naturally input in the system to convert rotation into translation. So this means, as I was saying, that our CQI is exactly, that column. And CQD is what is left of CQ when extracting CQI. Huh? Now, of course, since we have to go to express the delta, the dependent with respect to independent ones, you remember that at a certain point we have to invert CQD. So we must ensure that CQD is non-singular. How is that done? It's done being sure that our Jacobian has a full row rank. And how do we ensure that it has a full row rank? Ensuring that the 11 chord equations, so that the constraints are linearly independent. Okay, so if we are sure that the constraints equation are linearly independent, then CQ will have a full row rank, 11, and as a consequence, CQD will be non-singular. Okay?
Does that lead to any constraints in the structure of the mechanism?
We will see right away. So we finally write okay, so this is where we wanted to go. And so as you can see now, once we set the virtual variation of the independent one, so which is basically θ2, we get all the rest as a matrix multiplication. All the rest of the system of multiple bodies is determined. Now, the last thing that I wanted to show you today is something that answers to your question, to your colleague's question here. So as an alternative, let's choose R42 as independent coordinate or degree of freedom. So if you remember, R42 is the horizontal translation of the mass. For example, in this case, when you want to translate, if you want to convert translation into rotation. Okay? Correct. Yep. Correct. So in this case, so it's the fourth, sorry, it's the last, no, sorry. It's the third to the last column that you have to extract, okay, to get CQI. So it's this one. Now, if you look at what is left, so on the other side, CQD is what is left. And in particular, it becomes singular for θ2 equal to θ3 equal to 0. Okay, so if you go back here, you remove this column, and then you get CQD, and you put 0 to θ3 and θ2, you're left with a singular matrix. So CQD is singular. It means that you cannot invert it. Why? Well, let's see. What's the physical meaning of that? This is it. θ2 and θ3 are now 0. What happens if you try to slide the mass from left to right? Can you actually convert it to rotary motion? No. That's a singular configuration. This is called singular configuration. And that's why CQD cannot be reversed, inverted. Okay, so that's why, and it comes from the choice of the arbitrary, of the independent coordinate. Can be done arbitrarily. If you do it like this, because eventually, for example, in this case, you want to translate rotation, translation into rotation and convert, then you have to be aware that that may be the case that this conversion becomes not possible anymore, and you're stuck, and it's this the case. So, for example, you can do this. If you stay away from these values, then it's okay, but you need to know. Okay, so when you, again, the important concept of all these things is that the choice of the independent, of the degree of freedom is arbitrary, but it has consequences. So do it carefully. Okay, so this is and this is a singular configuration. For the other choice of the degree of freedom, so for the rotation θ2, you could actually observe that there was never the case in which CQD became singular. And in fact, if you think about it, physically, it makes sense, because as long as you rotate about 0.0, you never get a problem. You never get stuck. Okay, so from rotation to translation, no problem. The reverse, not quite. See, yep, you have to go through this. So it means that when you have this matrix and you choose, you should check for which values the determinant goes to 0. Okay, and then you have to check if those values of the coordinates are close to any operating condition that you want to experience for your mechanism. If not, fine. If so, you have problems. So this is a check you have to do. whenever you design a mechanism. Okay.
If it's a holonomic system.
I'm sorry, sir?
It's a holonomic system.
This is all okay. All this treatment is for holonomic. Huh?
So that's the first. Sure that it's a holonomic system.
Mm-hmm. No, what you do is, yeah, you go through this, you set your subset. Now it's only one, but it can be 2, 3, or whatever, number of independent parameters of degrees of freedom. This automatically lets you to the choice of the CQD. And then you have to see when the CQD determinant becomes 0, for which values of the remaining parameters. Okay. If your operational condition include those values, well, you have a problem. Okay, that's it. So if there is no additional question, I will stop the recording here.